welcome everybody, and thanks so much for coming today. So this is our last Oxford Energy Network seminar of this term, and I'm very pleased that you're all here. My name's Tina Fawcett. I'm the Oxford Energy Network convener, and this is Aaron, who's the coordinator of the network. As you probably know, since most of you come to these, we hold weekly seminars during term time, and if you look on our website, you'll see, and if you're on the newsletter, you'll see we've already got the list of speakers, apart from, well, one is slightly in doubt, but essentially we've got the next term speaker list already available. So you're able to sort of put that in your diaries now and join us next term. We thought we'd have the final session of this term. It would be nice to have a kind of a celebration of chemistry at Oxford and its contribution to the energy transition. And that's partly, well, it's largely because the timing of this talk is to fit with the Good Enough lecture tomorrow evening, which many of you may be going to, which again is a kind of Oxford, organised by the Zero Institute, and it's kind of a celebration of energy research at Oxford, and named after a pioneering chemist at Oxford who was very involved in developing the science for lithium-ion batteries. And so we've got one of his fellow collaborators, Professor Stanley Whittingham, is coming to speak tomorrow evening. But before hearing from the Nobel laureate, we're going to hear from three of our own chemists about the sort of, you know, what chemistry at Oxford is currently doing to sort of help further the energy transition. So we've got three speakers, three different types of chemists. We've got a materials chemist, an organic chemist, and a physical chemist, which is somehow different from an inorganic chemist. Anyway, well, you can explain. My last chemistry was A level. It's a long time ago. So they're all, you know, obviously. We're delighted to have all of them. I'll just give you a couple of snippets from everybody, because there's three of them. I can't actually remember this, so I'm afraid I'm going to have to read some of it out. So James Durrant is Professor of Photochemistry and Sustainable Energy in the Department of Chemistry, and he's also a Fellow of Magdalen College. And he's recently joined Oxford. In fact, he's sort of in transition from his previous place at Imperial and Swansea University. He was elected a Fellow of the Royal Society in 2017 and received a CBE for services to photochemistry and solar energy research in 2022. So that probably gives you a clue about what we're going to hear about from James. Next, we've got Dan Congrave, who's a Royal Society University Research Fellow and also a Senior Research Fellow at St John's College. And he's done various previous things, which you can see on our website. But he's looking particularly at problems holding back the applications of organic semiconductors. So I think we will be talking to some of that today. And then finally, we've got Robert Hoy, who's an Associate Professor in Materials Chemistry. He's also a Fellow of St John's and a Royal Academy of Engineering Senior Research Fellow. His research group focuses on inorganic semiconductors for energy applications, including metal halide perovskite nanocrystals. And he's also a CTO of Nanoprint Innovations. So obviously there's a lot of different sort of chemistry and exciting science in the room. And the way we're going to run it is each speaker is going to speak for 10, at most 15 minutes. And then I think what we'll do, unless there's any immediate questions of clarification, we're going to bring them all back together and to sit in front of us at the end as a panel to sort of answer general, you know, cumulative questions from everybody. So I think you're going first.
I am going first.
Okay, yes. Brilliant.
Oh. Thank you very much, Tina. It's very, very nice to be here. I am the newbie. And I feel a little bit daunted by being the newbie. I've been a recent appointment in chemistry, and chemistry's asked me to help coordinate some of their sustainable chemistry research, which is why I think I ended up standing in front of you today. I'm still learning what happens in Oxford, but I'm excited about the opportunity, and I will talk a little bit about it today. And so what I want to talk about particularly, is the idea of actually synthesizing fuels and chemicals, but in a sustainable way. And the way
you have to point it.
Right?
You have to point it towards.
You have to point it towards something. Maybe it's turned off.
It wasn't.
Probably that. Is that?
Oh, now try.
Oh, there we go. There we go. Oh, I can't stand there. It's all too dramatic. It's all too dramatic.
Yeah.
So this is an illustration of where chemistry is now in terms of chemical industry. That pretty much all the chemicals we use, all the polymers, all the fertilizer we use in our fields, the fuels which go into our cars and our planes come from fossil fuels. Mainly from oil, but of course also from gas, and there's coal and all this. But our chemical industry is basically fixed on fossil fuels. That is, that those fossil fuels are both the chemical input, that's where the carbon comes from in the polymers in nylon or whatever it may be. It's where the energy comes from, which drives the chemical transformations. But of course, those chemical transformations and those chemicals, when they're burnt as a fuel, contribute significantly to CO2 emissions. And if we're going to move towards net zero, we don't need just green electrons, and we're going to hear about green electrons in a minute. We're going to need to decarbonize our chemical industry, or particularly defossil fuelize our chemical industry. And that is a challenge which the chemical industry is only just beginning to get its head around. It's not a challenge which is currently being substantially addressed. It's kind of the next challenge which is going to hit us in the next 20 or 30 years as we need to decarbonize. And so there's a vision here from published last year about what the chemical refinery of the future is going to look like. And it's not going to have fossil fuels as the input. It's going to have biomass and waste as an input, but probably they are not at the scale fully needed to meet the full requirements. And it's going to have to use CO2. If we're going to have carbon products, we will have carbon products going forwards. A lot of that carbon is going to come out of the atmosphere. That's a whole interesting challenge, which currently we are unable to meet in a cost-effective way. And we're going to need to have some energy to drive those transformations. And that energy needs to be sustainable. Obviously, it's going to be renewable power. And so we're going to increasingly be talking about chemistry driven by electrons, by green electrons. I'm not doing anything. If I go here, I'll do it from here. So this is a vision of what the chemical industry might look like. Oh, that's working, brilliant. Going forwards. So it's a vision by a guy from Stanford, where you have the idea you have energy inputs, and those energy inputs will be solar cells or wind, or maybe nuclear, if you like nuclear, or hydro, or whatever. And you have chemical inputs, and those chemical inputs will be simple. They'll be carbon dioxide and water and nitrogen. And you harness this energy to convert these chemicals into useful chemicals. Ammonia as a fertilizer, for example. Currently, all the fertilizer we use is powered by methane, with CO2 release. It's about hydrocarbons. Of course, we want to use less fuel. And that's obvious, and that's why batteries are interesting. But we're still going to need sustainable aviation fuel. We're going to need some sort of fuel for ships, for trucks, all this. And that, we hope, should be sustainable. And then, of course, we also need the chemistry of converting what we would call these chemical feedstocks. Hydrogen is, of course, part of this story, into the chemicals which we use to make things in the future. And so the motivations are around, obviously, fossil fuel-free fuels and chemicals. One of the key motivations is that many of our renewable energy sources are intermittent, and we need to find ways to store energy, and the most scalable way to store energy is in chemical bonds. Batteries are good, but they're not so scalable. Putting the energy into methanol in a tank is far more scalable. It's also far more transportable. We're going to have a challenge that the regions of the world where we have a large amount of renewable power, of course, are not always where the demand is. And we're going to have to move energy around the planet. And the vision is we will still be having tankers full of hydrocarbons or maybe ammonia going around the world, shipping fuel around the world, but that fuel will be green fuel, where any carbon in it came from the atmosphere. And then we need to find ways to utilize CO2. We've got to do this all at scale. So, for example, we have to worry about rare earth elements and avoiding their use in these technologies. And we've got to do it cheaply. and that's a big challenge because fossil fuels are cheap. So this is about green hydrogen, it's about green ammonia, it's about what's sometimes called liquid sunshine. The concept that you can take the energy from the sun and turn it into a liquid fuel. And that currently is not yet realizable. But it's a vision which people are starting to have as an ambition. Chemistry is at the heart of much of that transformation. We're talking about chemical refineries, and so it's maybe not very surprising. Here's just some illustrations of where chemistry fits into that story. It's a substantive, if this happens, and if we want to meet net zero, it needs to happen. We are talking about transforming the chemical industry, and that's a substantive undertaking. And it's going to need a lot of innovation. Some is already happening, some is still to happen, and Oxford is already very active in many areas. Batteries is an obviously exciting area, and fuel cells. The downstream chemistry of converting biomass or using CO2 to drive the synthesis of polymers is a big area. We're going to hear about solar cells in just a minute, and that's exciting, a fantastic area. I'm going to talk little bit about harnessing the sun towards the end of the talk, directly to drive chemistry. That's my particular passion and excitement. This is just an illustration actually put together by Charlotte on some of the areas where the chemistry department is engaged in this challenge of contributing towards net zero. And some of it is the more conventional ideas of energy, which we hear a lot about through the energy network. But it's also around the challenge of catalysis, but catalysis driven sustainably, where the energy inputs are not fossil fuels, and where the chemical process associated with CO2 emissions. It also needs theory. Batteries, as I've talked about, is also important, and environmental chemistry is important. But of course, all of these topics are not chemistry alone. And one of the things that I'm just starting to get my head around is the wonderful and complicated ecosystem which exists in Oxford, with all the different aspects of sustainability and net zero, and having a zero institute and a net zero institute is one of the challenges I've had to get my head around and understanding. And the various networks, and now we have Oxford Earth, and that's all very exciting, and the Faraday Institute for batteries. So none of this is to say that chemistry is the answer by itself. But if we're going to transform a chemical industry and essentially industrial chemistry, that is going to involve a lot of chemistry. And I think that's an exciting challenge for the chemistry department. I think that's one of the reasons why they ended up bringing me here. There's already a lot of activity going on. If we just think about catalysis, then Charlotte's already leading two of the major UK centres looking at how we can have more sustainable catalysis and more so there's the catalysis hub, and there's the sustainable chemicals and materials manufacturing hub. These are UK flagships, and they're based in the chemistry department in Oxford. And they are very much contributing towards the next generation of challenges towards net zero. We talk a lot now about green electrons, and that's important. And we're going to hear more from Robert and Dan about green electrons, but there's challenges beyond that in the next 20 or 30 years, which I think are quite exciting. And these guys do loads of fantastic research. Charlotte's looking at how to make polymers using where CO2 is the input to make the carbon into polymer. Kylie's learning from enzymes, and enzymes in biology are fantastic at chemical conversions in ways that sometimes it's very hard to achieve with direct chemistry. Michael is a theorist, and he's increasingly looking at the theoretical chemistry of CO2 conversion, which I think is a big challenge. It's challenging to work out, because CO2 is not a reactive molecule, but we have to make it react if we're going to be able to use it in new fuels. My particular interest is inspired by plants. Plants, we hear a lot about CCU, carbon capture and utilization. Plants do carbon capture and utilization driven by the sun. They convert atmospheric CO2 into glucose, releasing the oxygen which we breathe, and the chemical efficiency is the order of 7%. That's pretty good. given that it's taking CO2 out of the atmosphere to drive in that conversion. The organism efficiency is far lower, which is why there's limits to how much biomass we can use in the energy technologies of the future. And so we need to think about other ways of doing it. I get excited about what we call artificial photosynthesis, which is the idea of chemical systems which harness the sun to drive chemistry. And this can be most obviously is solar cells and electrolyzers, and that exists. But currently, green hydrogen, and that's people get excited about green hydrogen, it's too expensive currently. Solar cells and electrolyzers, if you use those, but even if electrolyzer is free, the hydrogen is 3 times more expensive than the hydrogen for methane. That needs to change. Maybe we can change the cost of electrolyzers and solar cells. We'll hear about that. I'm excited about other ways of putting semiconductors and catalysts, light absorbers and catalysts together to drive function. It doesn't have the simplest water splitting. You can think about other chemistries, reducing CO2 and all this sort of thing. But the simplest idea is just having particles which drive chemistry on their surface. It's a vision which, if it works, you can have a slurry of particles which you shine light on them, chemistry happens on the surface, maybe you make films of them. The cost analysis suggests it should be cheap. Until recently, no one believed it would work, because in general, you excite these particles and the electrons in the holes don't drive chemistry, they recombine, because chemistry is slow, carrier lifetimes are short. They don't work. These are 2 minutes, perfect. These are sheets at the 100-meter square scale, where every photon which is absorbed splits water. So the quantum yield is 100%. And no one believed that was possible until these guys proved it. That is exciting. It's not yet useful because they're white. And so they don't absorb UV light. It's not very good if you want to harness the sun. But there's all sorts of research happening here about how we could develop new materials which can achieve visible light activity to make that chemistry work. So Ian's looking at organic semiconductors. Robert is not going to talk about it today, but he's working on artificial leaves with various inorganic materials. And Miller's looking at CO2 catalysts. Edmund, until recently, of course, very sadly, was working on rather exciting high temperature and pressure catalysis. And then we've got people like Claudia and myself who are interested in the kinetics. I get excited because now there's a whole raft of materials which are cheap and which we shine light on them and they make charges which live for seconds. I never expected that. No one expected that. And we are now starting to discover that there are materials, you shine light on them and the charges don't all. You can sit around long enough to get chemistry. And I think that could be quite transformative. I should stop there. I'm talking about things which currently are not technology primarily, but they are, I think, things we're going to need some ways of driving chemistry sustainably in the future, and that's going to need new science as well as new engineering. And with that, I'll stop. I pinched.
Right.
Robert's photo because I thought it looked rather good.
Nice photo. Okay, well, thank you, James, for getting us started and really nice introduction and overview of. So I'm going to take us into the solid state and talk about green electrons production using photovoltaics. So as we all know, this is very important when it comes to meeting our net zero targets. So we have the International Renewable Energy Agency, IRENA, and they published reports stating that we want to stay within 2 degrees Celsius of pre-industrial levels of carbon dioxide equivalent emissions, then increasing our deployment of photovoltaics, which takes sunlight to produce clean electricity, is a very important part of that. And they predicted that we need to increase the deployment from just under 1 terawatt back in 2021 to 8.5 terawatts by 2050. So for those of you who aren't familiar with PV, we'd like to talk about how many solar cells we deployed in terms of the peak power that they produce. And just for context, we now just about reached 1 terawatt after several decades of development. And you can see we now to exponential increase that to several terawatts by 2050 to meet net zero. So of course, this won't be cheap. So according to these predictions here, this requires 6 trillion euros of investment, not just for PV, but for everything else needed to reach net zero. But on the other hand, this brings about 150 trillion euros in terms of benefits, in terms of health, climate change related savings, mitigating worst effects of climate change. But of course, this is just one prediction, and there's other predictions which expect that we need to go much further, which we need a much greater degree of electrification in the future. So some other predictions even go up to 80 terawatts of PV. And within the UK, that's the context that we have that fits within that. So the most common technology that we have in industry right now is based off crystalline silicon. And a decade ago, everyone was saying silicon solar cells are too expensive. There's no way this can work. But then look at this trajectory in terms of the cost of these silicon solar cells at the time. And it says, feed time from Germany, because I've taken this data from that Fraunhofer Institute for Solar Energy, which has very rigorously tracked and monitored the price of solar electricity over time. And if you put this value here in context, this is even cheaper than onshore wind, even cheaper than fossil fuels as well. And in many parts of the world, solar energy is the cheapest form of electricity. But there's more we can do with it, and there's a lot of scope for new application development. So here on this slide is just a small snapshot of many different challenges that we need to address using chemistry, also other disciplines. So one of those challenges is that after 6 decades of development, silicon solar cells have now reached the limits in terms of their efficiency. So just a couple of months ago, LONGi, which is one of the PV manufacturers based in China, they published a paper in Nature where they got 27.8% efficiency from the silicon solar cells. And for context, within the PV community, we believe that 28% is the practical limit that you could achieve with this material. So it's remarkable that we've basically reached that limit. And I think it remains to be seen whether LONGi can engineer the devices to exceed our expectations. But broadly speaking, we can say that silicon has reached its limit. A problem here is that when it comes to the price of solar energy, the module itself only accounts for 1/8 of the total price. But most of the rest of the price comes from the balance of systems, comes from labor, profits, installation. So if we can't increase the efficiency further, we can't really decrease solar. And that is a big challenge. So even if we make these solar cells for free. So it's very important that we can find ways to overcome this 28% efficiency limit. And an approach that many people, including people here in Oxford, exploring is to make these tandem solar cells, where you have multiple different subcells that absorb light in different parts of the solar spectrum to convert a larger fraction of that energy into electricity, rather than wasting the energy from sunlight as heat. And currently, these perovskite silicon tandems are very promising. They've now reached 35% efficiency, which is greater than each of these subcells individually. But the application for solar is much greater than just putting them onto rooftops and making solar farms. We can use them for other industries as well. And one of the most important ones is for the Internet of Things. This is an ecosystem of many billions of devices right now. And this ecosystem is exponentially increasing. And some people predict we may have over 1 trillion of these devices in the future. These are small electronic devices that can communicate with each other. And an important question that we have to ask is, how do we power so many of these small devices which are autonomous? Right now, the most obvious way to power them is just using batteries. But if you have 1 trillion of these and just use batteries, they last for about a couple of years each. Then we have to either throw them away or recharge them. So this leads to a sustainability challenge and a practicality challenge, in the sense that if we are throwing away 100 billion batteries, there's a lot of waste created and creating a lot of work for a lot of people. And that practicality challenge may limit the growth of the Internet of Things ecosystem. So photovoltaics has extremely promising potential to step in here. And rather than just rely on batteries, we use PV to harvest the energy we get for free from ambient lighting and to power these small electronic devices autonomously. So instead of these batteries running out after 2 years, they're recharged constantly using PV by harvesting ambient lighting so they can last for 10 years. And this is the same concept as if any of you have used a calculator for a solar cell built-in, that calculator will probably not ever run out of energy because it's constantly being recharged by your solar cell. And if we take the calculator analogy, that is made from amorphous silicon. This is less than 10% efficient. Some of these newer materials that we'll be coming up with, including halide perovskites, can reach beyond 40% efficiency. So there's a big improvement in terms of the feasibility of using PV for energy harvesting. And James mentioned this as well. There's a lot of opportunities in terms of making use of the synergies between solar energy and photoelectric chemistry, making use of some of the things and device structure that we develop for PV to benefit green hydrogen production as well. Now, on the flip side of this, in addition to developing these materials and devices, we have to think about more and more what's going to happen at the end of life. If we increase the deployment of PV to the multi-terawatt scale to meet our net zero targets, then a challenge that we face is the amount of waste that's going to be created. And this is where it's very important for us to think about technologies beyond silicon, because if we rely on silicon only as our PV material, it's very hard to recycle these. You can't really reuse the silicon as a feedstock anymore. And so people predict that by 2050, we may have 160 million tons of electronic waste created. So this is where newer materials can become quite important. For example, we have organic materials, and we have halide perovskites, and other kinds of inorganic materials, which are much easier to recycle, which could be, for example, dissolved in water. And then you can then take those elements dissolved and then recycle them as a feedstock. So these are all some important chemistry challenges. So I'll just go into some of the main highlights of various technologies which are emerging and promising. So this paper study here is a roadmap paper that involved many people from the UK solar cells community. And what you see here is an image that captures a snapshot from the community about what's needed for this technology. So what's really quite remarkable about halide perovskite is that even though this material has been under development for just over 1 decade compared to 6 decades with silicon, it's now approached the same efficiencies as silicon. And this is technology that's now beginning to enter into the market. The question we have to ask is, what do we need to change to bring this to the market? And these challenges here go from the fundamental ink chemistry, how we make these materials, from the solution phase, the vapor phase, and also about understanding what's happening in these materials at the atomic scale and at the macroscopic scale. So having a hierarchical set of characterization to understand and link up what's happening across these multiple length scales. But then going further and thinking about some of the challenges to bring this to market in terms of encapsulation and improving the lifetime of these devices so that it could match the lifetimes, already very good lifetimes, we could get with silicon solar panels. And then this is another highlight, just to elaborate a bit more about this idea about indoor PV that I sort of briefly mentioned earlier. So the idea here, the concept here is that for each of these small nodes that you have as part of the Internet of Things, you have a way for these to communicate, but then you have this indoor PV panel attached to it that can harvest energy. And the size doesn't need to be very large. It only needs to be about 10 centimeters squared. So about the size of a credit card, and that's enough to harvest sufficient energy to power these devices under light. And this shows you the potential of some of the newer materials. So I mentioned that lead halide perovskites are now the most efficient indoor PV technology, with over 40% efficiency. But of course, the problem is that they contain lead, and these will be used in indoor settings where they're closer to the consumer. So even though you can use lead-based perovskite outdoors, there's no regulation against that currently. For indoors, it's important to develop lead-free alternatives. And a big focus of my group and many other groups around the world is to develop lead-free alternatives that can mimic some of the exceptional optoelectronic properties of halide perovskites. And this shows you a selection of some of these materials. So we call these perovskite-inspired materials. And earlier, we were sort of a little bit disappointed about how low their performance was compared to halide perovskites. But one of the reasons for that is because the band gap you can see here is close to about 1.9 eV, which is too wide to work as single junction solar cells. But if you bring them indoors you have white light LEDs. The spectrum is now still being a broad spectrum with most of it in the infrared. It's now concentrated in the visible. Suddenly this wider band gap becomes the optimal band gap. And you can see here, we calculate the efficiency limits. So that's the SLME for these various materials, and some of them can go beyond 40% as well. There's a lot of potential for some of these newer materials to be used for energy harvesting to more sustainably power Internet of Things electronics. And this is an example of one of these emerging materials that we've been working on. So this is an antimony sulfide. And here what we did, we grew this using a hydrothermal bath deposition method to increase the grain size. So what you see here is we use an electron microscope to measure the microstructure of these materials. And by adding a chelating ligand into the precursor bar, we're able to change how this grows to reduce the grain boundary density. And this allowed us to reduce the trap density and therefore that improved the performance. But here you can see the indoor PV performance at the 1000 lux, which is a typical luminance you'll find indoors. And that at that time was the record value for this particular device. But of course, we went further than that. We demonstrated, connected a few of these devices in series to demonstrate we power some of these electronics that you might find under indoor settings. So this multi-sensor platform is able to measure temperature, humidity, and pressure. And by being powered with this panel of antimony sulfide indoor PV, it was able to continuously measure this for several weeks in air and then communicate that information via Bluetooth low energy. So this is a demonstration of where we've gone in terms of fundamental chemistry through to electronic applications. But of course, there's not just inorganic compounds, there's also organic PV as well. So some of the people in the room here work on organic PV, and there's many different things you can do with these non-metal-based materials. And one of them, which I find quite interesting, is the area of agrivoltaics. Because of course, in the future, our population will grow. So there's going to be increasing competition for land between urbanization, agriculture, and energy production. Okay? In terms of, if you think about how much land space solar farms are going to take. So what if we could make more efficient use of land? What if you could, turn these greenhouses and integrate organic PV into them? And here you can see that certain organic materials are able to absorb the complementary wavelengths of light compared to chlorophyll. So here you have these filters on the organic PV on the greenhouse. It absorbs some of the sunlight, produce electrons, but then let through the other wavelengths of light, which chlorophyll needs to allow plants to grow. So this is where we can make more efficient use of land space. And this is a slide I took from Professor Ji-Sung Kim, who's sitting in the audience, sort of summarizing where organic PV is going. There's been a recent revolution or resurgence in the field in terms of increasing pace of efficiency development by making use of these new types of organic materials. So these are called non-fullerene acceptors. And you see a range of these going from fullerenes through to these non-fullerene acceptors. And you can see that has been responsible for this sudden uptick in the efficiency of these devices. But of course, the challenge across all of these different devices is that the maximum voltage you can produce is lower than the efficiency limit, but hopefully that this gap can be closed in the future. I won't go, somehow I have a very short time left, I won't go too much into detail, but in addition to these applications that I've spoken about, there's also a lot of importance and scope for fundamentals. And in particular, a particular area that we're particularly excited about is to develop materials that can tolerate defects. And I just want to illustrate this by comparing silicon versus lead haloperovskites. So here you can see silicon has a very low defect density. If you make these polycrystalline, then the efficiency you can get is 23%. Haloperovskites, millions of times more defects, and yet can reach much higher efficiency. And the reason this can come about is because these materials are able to tolerate defects. And you think this has quite significant implications in terms of how you manufacture these materials. You use much simpler and lower temperature manufacturing processes, which are greener and still get higher efficiency. And that means that the cost of manufacture these could be a lot lower as well. And that makes it a lot more compatible with having the manufacturing in multiple different places, not just concentrated in some areas. I'll skip over that slide and focus on some future areas. So a future area that we and others are particularly excited about is to go further in terms of understanding how defect tolerance comes about. And this requires a close synergy between modeling, between computational simulations, advanced characterization, and there's a lot of capabilities here at Oxford, spectroscopy, also microscopy, and linking these together to form a better understanding of how defect affect materials and how we can control the effects. And this is important not just for solar, but also for green hydrogen production, for catalysis more generally, as well as thermoelectrics we can use for decarbonizing heating and cooling. And in addition to these more fundamental aspects, there's a lot of potential for integrating AI and robotics into this process. So some of you may know that we recently have the Allison Institute of Technology, which just moved into town. It's based in the Oxford Science Park. And of course, they have a very strong AI team. And they are very interested in developing self-driving labs, currently for biology. But in the future, there's a lot of scope for applying these tools for biology also to chemistry. And going beyond just the solution-based method, but also to vapor-based methods, or integrating AI for accelerating the materials discovery and optimization process. So this gives you an idea of the landscape and the sort of scope that we work on across Oxford. The work on PV is not just in chemistry, but also across materials and physics as well, across multiple different areas from different technologies, both first generation and through third generation materials, as well as computations and spectroscopy. And across these different people, there's been a lot of success in terms of translating the technologies that we develop in the lab to the industry. And this is just a small selection of many different companies that we in the community have worked together with. I just want to highlight cluster tool. So see Professor Moritz Reed is here in the audience. So he's one of the leaders of this cluster tool based in physics, which is a multi-user facility. And there's a lot of scope here for automation and integrating AI to make this to a self-driving, to accelerate the sort of research that we're doing. So just want to leave it there. Thank you.
Great, thank you. Yeah, so I'm here representing chemistry. So I'll start by saying a little bit about semiconductors are so exciting and what we've achieved so far. And then I'll proceed and talk about one of what I think is one of the big fundamental problems that we really need to tackle if we're going to basically move organic semiconductors forward to make them better for electricity, light, into conversion. I really think that when it comes to the pathway towards solving this problem, that new structural chemistry is really going to be the first stage of it. Okay. So, as someone who works on organic electronic materials, it's a really exciting time to be in Oxford at the moment because not long ago there were only two groups working on it, Professor Ian McCulloch and Harry Anderson. But within the last year, this has really expanded, and there's now 6 groups working over in the chemistry department on the synthesis of these organic electronic materials, or working in complementary areas. So I think it's really worth putting substantial effort into trying to get organic semiconductors to work well. And that's because there's this really amazing potential to make our high-value electronic materials from carbon-based feedstocks. In principle, plentiful, renewable, recyclable. Additionally, these materials are really great when it comes to processability. So we can make films from solution, thin films, we can make flexible things. So there's a real, there's lots of great potential there to really implement these materials into our everyday life. But the thing that really excites me about semiconductors, which I think is the real advantage, is that it's really this amazing position to exploit the unique synthetic chemistry. So organic chemistry in this amazing position when it comes to structural diversity. So here we can see these little dots, these are carbon atoms. Well, it's possible for us to synthesize organic materials in 1, 2, and 3 dimensions. There's a really wide range of different molecular shapes that we can access. So we have this amazing level of breadth when it comes to where we can start when designing our molecules. It's as if we're only really limited by our imagination. And I think the important thing here is if you have breadth in structure, then you'd hope that would also lead to breadth in property. But the real beauty of organic chemistry isn't just in its breadth, it's also in its depth. I think you can argue that organic chemistry really is kind of the deepest sort of chemical discipline. Why? Because say we take a molecule that's kind of doing what we're interested in, well, we can now really refine the structure on a molecular scale, like atom by atom. So we can start to really fine tune and perfect it to get exactly. But I guess the real reason why I wanted to highlight this cool combination of breadth and depth that you get from organic chemistry is you can argue that the sort of space we can explore in terms of structure and property is quite endless. Or at least I don't think it's completely unfair to say that if you take any of the big sort of prolonged problems that are facing organics, it should be possible to solve them. It's just that we haven't made the right molecule yet. Right. So organic light emitting diodes are, I guess, probably the one big success story of organic electronics. I'm really interested in the interaction of organics with light, and it's this application that got me interested in organic electronics. So OLEDs are now commercialized, and they're really the dominant technology in smartphones. And if you look at the evolution of these devices over the years, this is clearly a collaboration between chemists, material scientists, physicists, engineers. But I think it's reasonably fair to say that whenever we've had a big step change, so from generation 1 fluorescence to generation 2 phosphorescence, further on, this has always kind of initially come from a step change in molecular structure. So all of these big advances came from a chemist in an academic lab, made an interesting new molecule which allowed us to explore the new structure property space. And so I think this should be a really nice poster child for what chemistry can do in materials applications and so the development of the OLED. And so, yeah, they're commercial now, but it took 20 or 30 years from when interest really started to spike to get efficiency devices. So why it takes so long, what were the problems? Well, there were plenty of problems, but I think one big problem that chart about bit was the problem of non-radiative loss. So wasting out energy as heat rather than converting it to light. So if you want to think of what the structure of an OLED device, we have an anode, and a cathode, and then sandwiched in between them are various semiconductor layers. So these arrows here are electrons. So when we turn the device on, the first thing that happens is we remove an electron from our highest occupied molecular orbital. So that's your valence band. And then we inject electron to our lowest occupied molecular orbital, so our conduction. And these charges will hop until eventually they meet in what we call the emissive layer. So they recombine, and this will generate a luminescent molecule in its excited state. So we call this an exciton. It's a whole electron pair. Ideally, we combine right. The real important thing to note about this whole process, charge recombination is something that's quite important in organics. So we're taking one electron out of this orbital and put a different one up here. So you have 2 spin half particles. And so these can occupy what we either call a singlet excited state, where they're completely opposing, or triplet excited states, where they are parallel. And the real key thing here is in charge recombination, we get spin statistical distribution. 25% of the time we get a singlet, 75% of the time we get a triplet. And this is really problematic because the singlet's going to emit light, but the triplet's don't. So our original OLEDs, our first generation ones, 75% of the time, whenever we made an excited molecule, we just lost our energy to non-radiative loss. And so we spent 20, 30 years figuring out ingenious ways to trick molecules into converting the triplets into light, like phosphorescence, and the activated lasers. Okay. So an interesting thing to always remember is organic light emitting diodes and photovoltaics are equal and opposite. So if we've been able to come up with a way to commercialize OLEDs, so to convert light to electricity efficiently enough to commercialize, then why have we not done this for the inverse process of PV? And so I think there's obviously loads of reasons for this. And one important one to remember is that our phones are really high value items. And so if the display costs quite a lot, it doesn't, it's not a complete deal breaker. Whereas as Robert was just saying, OPV needs to be super cheap. So I think that's a big one. But I'm going to talk a little bit about one of the more fundamental scientific reasons that we can try and tackle it. And this is back to I think I stole from Robert and geez, yeah. So it's all down to this idea of non-radiative loss in the near infrared. So I was just talking about OLEDs. We've got really good when it comes to red, green, and blue, so visible organic molecules, completely removing non-native loss. That's why OLEDs work efficiently, and you can see that here. When we have a band gap in the visible, it's basically just right on the shock requires, so there's like almost no non-native loss. When we move into near-infrared band gaps, this gap gets bigger between our ideal and where the molecules are. So yeah, this is really the key, is how do we get around this problem here of non-native loss? And I think the way we need to do that, similarly to what I just showed for OLEDs, is we need a new generation of materials designed for them. So the way I'm kind of approaching this problem, and I think we all should, is to get these good absorbers, we should optimize them as emitters, because we don't want to be wasting any energy. And so the people who are typically working on OPV need to start talking about people who are interested in emission. So here we have just a little bit of some really sort of preliminary data from some molecules we've been interested in the group. So this is very scientific, very fundamental. The point is, we have here, we've seen it already, a very state-of-the-art organic photovoltaic material. A new molecule. And you can see this is where they absorb, so they kind of absorb in the near-infrared similar band gap. And the problem with this efficient molecule here is it can't deal with these triplet states. Right? So if you start making triplet states with charge recombination in your OPV, they're just wasted. That's where your non-native loss comes from. So if we were to make like an idealized OLED from this, this is not a number that's been measured experimentally, but we'd get about 2%. Efficient. No, these are the wrong slides. We'd get about 18% for this. Sorry, we get about 18%. Whereas here's a molecule we developed in my group, and because the triplet states aren't a problem anymore, we've engineered the molecule to have these nitrogen boron atoms, gets rid of that issue. We can now start to get potential maximum efficiencies of 30%. So if you could implement this sort of molecule properly into organic photovoltaics, you should get less non-native loss. But yeah, so I think the summary really is, I think we can solve the problems in OPV, but we should probably start approaching them a little bit more with the lessons that we've learned from OLEDs. Yeah, so thank you very much.